Okay, so we've talked a little bit about the Schrödinger equation and the quantum mechanical description of the hydrogen atom. And without getting into too much detail about the math involved, because again, it's beyond the scope of our class, uh, we can say that the wave behavior is described by the wave function psi, and the probability of finding an electron in a certain area of space is proportional to psi squared. That psi squared is called the electron density. So when it comes to defining where an electron is at any point in time, it's impossible to do that. So we work in probabilities. So quantum mechanics then is going to define the region where the electron is most likely to be at a given time. So the Schrödinger equation, if we take a much broader look, is going to specify the possible energy states that an electron can occupy. And again, this is all done with the simplest atom, the hydrogen atom. These energy states, as well as the wave functions, are going to be characterized by a set of what are known as quantum numbers. Okay, and we're going to talk a lot about these here in the next few minutes. These are going to help us define several things, the shape of the space where the electron could be, as well as some other properties of the atom and of the electron. So instead of referring then, one big change compared to um, the Bohr model, we said that with the planetary model that Bohr used, we had the orbits that describe the energy levels, or how far away the electron could be from the nucleus. So instead of using orbits, we're not going to be using orbits. We're going to be using these quantum numbers and the wave functions that are going to describe what are known as atomic orbitals. Okay, so this is a change. It's not a big change in terms of the word, but it is a big change in terms of how we are going to define or to characterize where an electron could be. So we're using the term orbital, atomic orbital, rather than orbit, even though we can use some of the same principles from the Bohr model. All right, so our quantum numbers then, these are going to be needed to describe where electron density is distributed in an atom. And again, electron density would be an indication of where the probability, the high probability of finding an electron is going to be. So there are three quantum numbers that can describe an atomic orbital, and then there's a fourth that describes a property of the electron that we'll see a little bit later on. Okay, so there are a total of four quantum numbers. Three describe the atomic number. So the first one is called the principal quantum number, which we abbreviate as lowercase n. Okay, so principal quantum number n designates the size, and you can think of n as sort of analogous to, or similar to, even though it's not the same thing, similar to the energy level or the shell or the orbit in Bohr's model. Okay, so it's not the same thing because we've dispensed with the term orbit. We're going to be using orbital from now, but the principal quantum number n is the same n that we talked about previously. The second quantum number is known as the angular momentum quantum number. This is abbreviated lowercase l. Okay, so make sure that's lowercase n, and that describes the shape of the orbital. So we'll see several different shapes. So for example, is it spherical? Is it whatever? We'll see some other types. And then the magnetic quantum number, which is abbreviated m, lowercase m subscript lowercase l. So m, we say m subscript m sub l is how we would refer to that quantum number. And that specifies the orientation of the orbital. Okay, so the orbital, is it oriented along the x, the y, or the z axis, or maybe between the axes, etc., and so on and so forth. Okay, so again, just to sort of recap, the atomic orbital as in a broad sense of the word, is a region of electron density, okay, where there's a high probability of finding an electron. And we have three quantum numbers that describe that atomic orbital. Principal quantum number n is the size. Is it big? Is it small? Is it whatever? The angular momentum quantum number, which is L, lowercase l, that describes the shape, spherical or any other shape. Magnetic quantum number m sub l tells us the orientation. Is it along the axes? Is it between the axes? Is it in a combination of the axes? Etc. Okay, so let's take a look at each of these in a little bit more detail. The principal quantum number n designates the size of the orbital, and there's a very simple relationship. Larger value of n corresponds to larger orbitals, and the values for n are whole numbers. Okay, so integral numbers that go from, so n could be 1, 2, 3, 4, etc. Okay, it starts with 1 and it goes in whole number increments. The bigger the value for n, the larger that orbital is. Okay, so that's something to keep in mind. The value of n, like we mentioned before, corresponds to the value of n in Bohr's model of the hydrogen atom. All right, so we can say then as n increases, as our principal quantum number n increases, right, the energy of the orbital increases as well. The distance from the nucleus increases, right? And then the larger, obviously, then the orbital is. So when we have orbitals that can be described by these three different, or actually four different quantum numbers, if the orbitals have the same n value, we refer to those as a shell, a collection of orbitals with the same n value. So if they all have n equals 1, then they're part of a shell. If they all have n equals 2, all of those will be orbitals will be part of a shell. Okay, so n is the shell number. It's the principal quantum number that tells us the size of the orbital. The angular momentum quantum number describes the shape of the orbital, and these are the values are also integers, so these are whole numbers, whole number values that depend on the value for n. On the principal quantum number. So the allowed values for L range from 0, so they go from 0 to n minus 1. Okay, so for example, if I'm talking about the n equals 3, principal quantum number, well, then the values for L could be, so we always start with 0, because you go from 0, and then we go to n minus 1. Well, what's n minus 1? Well, n minus 1 is 3 minus 1, which is 2. So we go from 0 in whole numbers, 1, and then 2. Okay, so those are the possible L values. So 0 to n minus 1. Similarly, if I'm just looking at, let's say if n is equal to 1, well, then L could be, we always have a 0, okay, and then what is n minus 1? So n is 1, minus 1 gives me 0. Well, I already have that here, and there's only one L value, which would be 0 in this case. Okay, and we can do that for all, all the integer values for n, the principal quantum number. So L depends on the value for n. And whatever value for L we describe, we can use a letter to designate that particular angular momentum quantum number, and that tells us the shape of the orbital. So if L equals 0, like it was before, we say that that's an s orbital, lowercase s. Okay, and then this describes the shape, remember. If L is equal to 1, then we say that's a p orbital. we're referring to the p orbitals. If L equals 2, we say that's a d orbital, lowercase. These are all lowercase. And if L equals 3, we're talking about the f orbitals, and a collection of orbitals with the same value of both n and L, those are known as subshells. So you may be wondering, oh, where does the S, the P, the D, and the F come from? Why do we call them this? Well, again, that's maybe beyond the scope of our class, but we can use a little bit of a mnemonic here to help us figure out the shapes, right? Because we're talking about the shapes of the orbital. So you can think of S. S kind of is the first letter in the word spherical. Okay, so s orbitals are spherical. P, first letter in the word propeller. So p orbitals are propeller shaped. D, so you think about the flower, the daisy. So these are daisy shaped, and we'll see these shapes here in a second. And then F, we'll see a little bit later on. Let's just say this is a fancy daisy. So F there. Okay, so as we go from the S, the P, D, and the F, the shapes actually become more complicated. And again, these shapes that we're going to see, these are not just things that we make up. These are solutions to the quantum mechanical treatment, or the quantum, or the math involved in quantum mechanics. So it's not just we're pulling these out of thin air. These are actually based on calculations, etc. All right, so we have N, the principal quantum number. We have L, which is the angular momentum quantum number that describes the shape. And then M sub L, magnetic quantum number. So the L is the angular momentum. M sub L is a magnetic quantum number. This describes the orientation of the orbital in space. So in which direction is it pointing, in other words? So just like N, the N value determines the L value, well, then the L value determines the M sub L value. So the M sub L values can go from, they depend on the L values. So M sub L values can be from minus L through 0 to positive L. Okay, so for example, and we can chart this all the way through. If n equals 1, okay, then my L value goes from 0 to n minus 1, and we saw before that the only value there is 0. And then my M sub L now goes from negative L, well, negative 0 is just 0, through 0, which is also 0, to positive L, which is positive. So M sub L is also only equal to 0. Okay, and that's for the first principal quantum number n. N equals 1. But what about if n equals 2? Okay, well then our L values go from 0 to n minus 1. So we have 0, obviously 2 minus 1 is 1, so we have 2 values for L. And of those 2 values now, we have 2 sets of M sub L values. So for L equals 0, the M sub L value here can be 0. That's the only option. But then for L equals 1, we have our M sub L values go from negative L, so negative 1, through 0 to positive 1. Okay, and these are also integers. They can be negative integers or positive integers. So we have 3 M sub L values. In the case of for L equals 0, we just have 1 M sub L value. And we can do that for the other quantum numbers as well. So let's just do the last one here. If n equals 3, okay, my L values could be, so L could be 0. It goes from 0 to n minus 1, right? So n minus 1 would be 2. So we have to go from 0 to 2. So we have to go through 0, 1, and then 2. And then for now, my M sub L values Uh, for L equals 0, just like above, M sub L will only be equal to 0. For L equals 1, my M sub L can be -1, 0, and +1. So we're going to have 3 of these M sub L values. And then for, sorry, and L equals 2, now I have -L, so -2, and I keep going, increasing by 1 every time. So -2, -1, 0, +1, and I go to positive L, which should be +2 in this case. So now I have 5, 1, 2, 3, 4, 5 M sub L values. So we can predict just based on the rules that we have here, we can predict we have an N value, we can predict what the L and the M sub L values are going to be. Similarly, we can work backwards and say, well, what's actually possible? What are possible quantum numbers if L equals 2, right? Is a M sub L value of -3 possible? And the answer would be no, right? You would have to have a L value of 3 to have an M sub L value of -3 or +3. So you want to think about these systematically. I know the first time you see this, it can be, sort of confusing, but if you slow down and you do it one step at a time, okay, it's going to make sense. I guarantee you that, but you have to not jump in, just take your time and ease into it. So one thing to realize now, we talked about this before, okay, if your L values are equal to 0, then we have the s orbitals. If your L value is 1, we have p orbitals. If your L value is 2, we have d orbitals. L value is 3, we have f orbitals. So now we can go ahead and we can assign those to these different numbers that we came up with. And we'll just finish this off here with if n equals 4. Okay, then our possible L values could be 0, 1, 2, and 3. And then our M sub L values for each of these then are as follows. For L equals 0, we only have 0. For L equals 1, we have -1, 0, and then +1. So we have a total of 3 M sub L values. For L equals 0, we only have 1 M sub L. For L equals 2, we have -2, -1, 0, +1, +2. So we have 5 M sub L values, just like we did in the example above, right up here. And now the only new thing is for n equals 4, we have another L value, and L equals 3. Now we start at -3, we go -2, -1, 0, +1, +2, and then +3. So how many M sub L values do we have here? 1, 2, 3, 4, 5, 6, 7 M sub L values. Okay, so these, remember now, the M sub L, they give us an idea of the orientation of these orbitals in space. And they actually also, by extension, tell us the number of these orbitals that we have. Okay, so for example, and if I go back to my n equals 1, it's my first energy level, I only have one L value, 0. And based on that, I only have one M sub L value. So this here, when your L equals 0, this corresponds to the S. And this here, we only have one M sub L. So that means there's only one S orbital in the first energy level, right? N equals 1. So we call that the 1s. It's the first energy level, n equals 1. That's this first number here. Okay, and then the s is going to tell us that our L value, right? That's our s that we have. And then there's only one of these because we only have one M sub L value. And that's s there, remember now, is spherical. Okay. If we look at n equals 2, okay, we're going to have two L values. Okay, so n equals 2 now. We have an L equals 0. An L equals 0 corresponds to an S, so we're going to have now a 2s orbital. How many s orbitals do we have? We just have one because we only have one m sub l value. But in this n equals 2, we also have a L equals 1. Well, L equals 1 corresponds to a P. So now we have a P, and it's in the second energy level, so it's a 2. And how many P orbitals do we have? Well, we have a total of 1, 2, 3 values. So we have 3 P orbitals. And the way that we designate them is by using the subscripts, so 2P, and then they're oriented along the different axes. There's a 2P along the x-axis, 2P along the y-axis, and then a 2P along the z-axis. Okay, so the 2s and the 2p, they belong to the same shell, same energy level, which is the n equals 2 energy level. If we go to n equals 3, then again, we're going to have L values of 0. Okay, so L value of 0 means it's the S, so we have a 3S. We also have an L value of 1, which corresponds to the P, and we have a total of 3 of these numbers, so we have 3 of these P orbitals. Okay, the 3px, 3py, 3pz, just like above. And now, in addition to these, we have L equals 2, and L equals 2 corresponds to the D, the lowercase d. So we have a D, that's in the third energy level, so that's a 3D. And how many of these 3D orbitals do we have? We have 1, 2, 3, 4, 5. We have 5 of these orbitals. And then finally, for n equals 4, okay, we are going to have the L equals, you always have the L equals 0. So this would be an s orbital. We just have one of them, and that would be the fourth, or the 4s. We also have L equals 1, that's a P. And that's in the fourth energy level. Okay, so we have a 4P, we have 1, 2, 3. We have 3 of these, just like we've seen for all the P's. If you go back and look at all of them, we always have 3 P orbitals, with the exception of the first energy level, because we didn't have any P orbitals there, because we only had one value for M sub L, and only L was only equal to 0 there. So that defined just the S sub level. In addition to this, now we have the L equals 2, that corresponds to D. That's the fourth energy level, and then we'd have 5 of these. And then now we have L equals 3, that corresponds to the F, that's in the fourth energy level. We have a total of 1, 2, 3, 4, 5, 6, 7, just like we did before. So we'd have 7 of these F orbitals. Okay, so when you go through and you look at these numbers, you want to pay close attention to what they're actually telling you. So we've seen 3 quantum numbers. The fourth one that we can define is called the spin quantum number. And this is expressed as M sub S, the spin quantum number. And this specifies, as it says, the electron spin. So when you have an electron, which remember now has a negative charge associated with it, it's spinning all the time. And when you have a spinning electrical charge, it actually generates a magnetic field. And that magnetic field can be pointing either up. Okay, so we say spin up, where the north is at the top and the south is at the bottom. Or it can be, the magnetic field can be pointing down, in which case we call it spin down. Okay, so spin up is designated, we designate that as a +1/2. If it's spinning down, we designate it as a -1/2. Okay, and that results from the charge electron spinning, generates that magnetic field. And we can actually identify that just by doing a simple experiment. Okay, if we pass the, an atom beam through a screen and we subject it to a magnetic field, we'll see that half of the electrons are deflected upwards, half are deflected downwards because, of their spin, right? Spinning up versus spinning down. So we have 3 of the quantum numbers that tell us, give us some information about the orbital. So the principal quantum number n gives us the size, the angular quantum number L gives us the shape, and the magnetic quantum number M sub L gives us the orientation. So when we write out our quantum numbers, we're going to see them existing in these types of forms, right? So we need to know what these look like. So for example, in the case here, let's say I have 2p subscript x. The 2 here tells me the n value, right? So n equals 2. That's the principal quantum number. Okay. So that's sort of like the energy level or the shell, if you will. P here gives me the angular momentum. Quantum number. And you can think of this as sort of the subshell, and then the X gives me the orientation. The fourth quantum number, m sub s, is just going to tell us a little information about the direction of the spin for that particular electron. Is it spinning up? Is it spinning down? So if we take a look now at how these atomic orbitals differ from each other, we're going to see some important differences between them. So for example, if we look at the differences between a 1s orbital versus a 2s orbital versus a 3s orbital, okay, first of all, we can see some similarities. They're all s's, right? So they're all going to be spherical in shape. The difference, though, is their principal quantum numbers, right? And we said that this is an indication of their size. So they're going to be different in size. So the 3s is going to be larger than the 2s. The 2s is going to be larger than the 1s. And if we take a look at the probability density, so psi squared, for example, we can note some differences between these, right? So as you radiate out from the nucleus, we can see the probability density, starts off at a maximum, then it decreases the further away you get. This is for n equals 1, okay, and L equals 0. For n equals 2, the second energy level, the 2s, so this here is for the 1s, this is the 2s, and this is the 3s, right? We can see that in addition to that, what we had originally here, there's another peak, and then we have a node, right, where the probability is 0, finding an electron there. And that corresponds to this region right here. So this is a 3D cross section of your atom, of the orbital, to be more precise. So then we have another peak as we go with the probability density right about here. And then for the 3s, right, we can see now there are actually 2 nodes corresponding to these 2 regions. And obviously now, you have your orbital that's a lot bigger than the 2s and the 1s as we go across. Now, what's even more, and we have 2 nodes here, I'm sorry. What's even more helpful, the radial probability distribution. So that's, for example, taking a look at concentric circles or concentric spheres as you go out from the nucleus and seeing what's the probability of finding an electron in that particular concentric sphere around the nucleus as you go from the center to the outside. And that actually now is going to give you more of a, well, there's a high degree of probability of finding an electron in one place versus another place. So if we take a look at this first one here for the 1s, okay, all we need to do is to look at the peak of this radial probability distribution right about here. That's going to be the most probable distance that the electron can be from the nucleus, right? So wherever this is the highest, this is going to be the most probable location, most probable distance of the electron from the nucleus. And this is for the 1s, right? So it's, just under 1 angstrom from the nucleus. For the 2s, right, what we'll see that, yes, it can be maybe here, about just less than 1 angstrom away, but it's way more probable for that 2s electron to be about just over 3 angstrom away from the nucleus, because that's the highest radial probability distribution, right? So most likely the electron is going to be about 3 angstrom from the nucleus. And then for the 3s, right, we'll see that the peak here is even further out. So this is about 7. angstroms. That's the most probable distance of the electron from the nucleus. Yeah, it's possible for it to be closer, but it's most likely to be about this distance away from the nucleus. So that's how you read these radial probabilities distribution. Okay, so we've taken a look at, the different quantum numbers. We talked about S being spherical. P, we said, the p orbitals that belong to the p sublevel, these are propeller-like, going to be our way to help us remember these. And these are oriented along the axes, okay? So this here on the left side shows you that probability window, that probability density maps. You can think of it as like an electron cloud. And all we do is we just put a line around where that highest probability is. And you end up with something that kind of looks like this, sort of an hourglass shape or a figure of 8 or an infinity sign. And for the p orbitals, remember now we have 3 p orbitals. And they're oriented along the axes. So there's one oriented along the x-axis here. Okay, so that's this one. There's one oriented along the y-axis, so that's the py. And there's one oriented along the z-axis, that's the pz. So if you actually superimpose these on top of each other, which is what you're having, you'll end up with it looking something like this, which looks way more complicated if you put all 3 of them on top of each other. But that's how they actually look. Okay, so those are all 3 of the p orbitals superimposed on each other. And again, they correspond for L equals 1 value. We have -1, 0, and +1, right? So 3 of these correspond to the 3 p orbitals. The d orbital, so again, d here, we can think of as being daisy-shaped. Okay, so they're a little bit more complicated than the p orbitals, and they correspond to L equals 2. Okay, so for L equals 2, or m sub L, orientation for these orbitals will be -2, -1, 0, +1, and +2. So we have 5 of these d orbitals. Okay, so we have the d, and the 3 here corresponds to the third energy level, dx squared minus y squared. Okay, so you can see these being oriented along the x and y axis. We have the dz squared, which looks very different than the others. We have the dxy, sort of in between the axes. We have the dxz, and the dyz, and so on and so forth. So we have 5 of these, right? 1, 2, 3, 4, 5. That corresponds to the 5 m sub L values. And then we don't have the F on here, but there are going to be 7 of those F orbitals. Okay, so let's say for L equals 3, okay, we're going to have M sub L values of -3, -2, -1, 0, +1, +2, and +3. So 1, 2, 3, 4, 5, 6, 7 d orbitals. Okay, and when will we encounter d orbitals? Well, we only get there when L equals 3. So in order for us to have L equals 3, we have to have go all the way up to n equals 4. The 4th energy level is what is going to have those d orbitals. Right, you can't have d orbitals in the n equals 3 because you only go, your L values can only be 0, 1, and 2. All right, so when we plot the energies of our orbitals and energy levels and subshells, for instance, on a chart, we can see how they vary, how they change from each other. So let's take a look down here at, hang on one sec, back up. So for the first one, okay, so we've seen that in the first energy level, there's only one orbital, that's the 1s orbital, and that's the lowest energy orbital that we have, the 1s. As we get further and further from the nucleus, right? So we have so this is n equals 1 over here, n equals 2, just like in the Bohr model, right? We get further from the nucleus, more energy associated with them as well. So the n equals 1 has just the 1s. For the n equals 2, we have the 2s, and we have 3 of those 2p orbitals. So this collectively we call the second shell for n equals 2. And then here, we call this the 2p sublevel or subshell. Right? And it contains or has 3 p orbitals. For n equals 3, we have 3 different subshells. Okay, so you can think of the n equals 3 being the third shell. We have 3 subshells. We have the 3s subshell, which only has 1 orbital, right? The s subshell is always going to have just 1 orbital, right? For the n equals 2, we just had the 2s subshell with 1 orbital to 2s, and we had a 2p subshell with 3 of those p orbitals. N equals 3, we have 3 subshells, the 3s with just 1 orbital, the 3s orbital. We have the 3p subshell with 3 of the p orbitals. We have the 3d subshell with 4 of the d orbitals. For n equals 4, guess how many subshells we have? We have 4 subshells. The 4s with 1 s orbital, the 4p with 3 p orbitals, the 4d with 5 d orbitals, and now the 4f with 7 f orbitals. Okay, so each shell, each energy level can be broken down into subshells, S, P, D, or F, and each of those subshell has a certain number of orbitals. Okay, so we have our shells, we have our subshells, and then we have our orbitals. That's sort of the hierarchy when it comes to trying to identify and pinpoint the location of electrons. So the shells are the n values, 1, 2, 3, 4th shell. Subshells are the s, p, d, f subshells, and the orbitals, how many? Of the s, p, d, and f we have. So to summarize, we can take a look at an example of a question. Let's jump down to here. Okay, so it says list the n, l, and m sub l values for each of the orbitals in a 4D subshell. Okay, so let's take a close look at the 4D subshell. So the first number here gives us the n value. Okay, so this tells us right away that n equals 4. Now the d value, or the d designation itself, right, where does that come from? Well, that is the L designation. So for our, for n equals 4, remember now L can be anywhere from 0 to n minus 1. So 0, 1, 2, and then we have 3, right? So these L here correspond to, the 0 corresponds to the S, the 1 corresponds to the P, the D the 2 corresponds to the D, and then the 3 corresponds to the F. So what is D equal to? Well, in this case, D, which is the L value, would correspond to 2. So L would be equal to 2 in this case. So our M sub L then depends on the L value. So M sub L goes from negative L all the way to 0, all the way to positive L. So our M sub L then can be negative 2, negative 1, 0, positive 1, and positive 2. So we have, just as in any of the D subshells, we have a total of 1, 2, 3, 4, 5 of those D orbitals.